Hello, let's take a look at a screen recording. I thought that we could try this in order to save ourselves some time, just because we might be running out of time with taking up homework questions and then on top of having another class that we have. So our time might be a bit short, so let's go through this so that you guys can just watch this on your own, and then we can sort of move on without having to deal with any tech issues or something that comes up or just distractions. So let's take a look at, this is lesson number 4 from Unit 1 for Dynamics for the 4U course. We're going to talk about frames of reference and relative velocity. Homework questions up here, can find those in the 4U space for the solutions, have some solutions posted for these homework problems. This note will still exist, and so you can take a look at this closer if you'd like, and you can follow through on your own as you watch this video. Great, so we're going to start with relative velocity. So what exactly is relative velocity? So we say that a frame of reference is a coordinate system relative to which motion is described or observed, right? So this key thing here is called frame of reference. That's going to be important for the course, going to show up again in unit number 5, right? So all it is a coordinate system, and we're describing motion relative to two different things, right? So for example, are we moving right now, right? So if you think about where you are sitting or where you are in space while you're watching this video, are you relative to a point on the floor, are you moving, right? Or based on your place in the solar system, right? So relative to the floor, you're probably not moving, you're just sitting there watching this video. But what about in the solar system, right? Are you moving then, right? So maybe the answer here is no, but maybe the answer here is yes, right? So it all depends on the point of reference, because obviously in the solar system, the Earth is moving around the sun, right? So depending on where you look, you can say that you're moving. Now, we can talk about what's relative velocity. It's normal velocity, but we are going to specify a reference frame for it, right? So, for example, we can use the symbol V sub or subscript BA, right? So this is the velocity of some object or something B relative to A. So notice that the B comes first, the A goes second. So the velocity of the object moving is what comes first in the subscript, and then the point or other object that we are using to reference the motion of the first object comes second. So again, V sub AC shows the velocity of A relative to C. So these can be points, they could be objects, they could be anything. So we use the subscripts to sort of indicate, and they go in that order. The first subscript is the object whose motion we are describing, and the second subscript represents the reference point or the reference frame that we are looking at the object motion. So to find the velocity of anything B, so relative to some other object C, we simply add the known velocities together, right? Just like our regular vector addition. We can add them together to find these two velocities to determine how they work together, because we can see that our rules for adding vectors together, when we put velocity of B relative to A, our first vector here, when we put B relative to A is our vector going up, and when we put the other vector A relative to C, when these vectors are tip to tail, the resultant vector that will be drawn when we add them together will go from the tail of our first one to the tip of the other. That gives us our resultant vector B sub C. Notice the placement of these two vectors. We can, in order to help us determine the resultant vector, which is BC, we have a B on the left and then a C on the right for the other two vectors inside. And then we notice that they both have an A on the inside, if that makes sense. So we can see that the green letters go on the inside, and we can imagine that it's like these A's are getting canceled, and then our B and C can go together, giving us the resultant vector there. This is helpful for when you're trying to determine what vector you're looking for given the vectors you have. Let's take a look at some examples. So they're vector quantities. We can draw vector diagrams to solve for two-dimensional problems. So we may come up with situations where some vectors are not moving in the same coordinate. So in this example here, VBA moves in the y plane, VAC is moving in the x. Our resultant vector is a combination of x and y. Example number 1. Passengers on a cruise ship are playing shuffleboard. Shuffleboard is just sliding discs on a smooth surface, just like curling, but not on ice. The shuffleboard disc velocity relative to the ship is 4.2 meters per second forward, and the ship is traveling in the same direction as the disc at 4.6 kilometers per hour relative to the Earth when the water is stationary. Determine the disc's velocity relative to the Earth. Things to point out. We have a cruise ship, or to be more specific, we just have, or less specific, we have just a ship. We'll just call it some sort of ship. It's on water, and people are playing shuffleboard. Then we're interested in the motion of a disc of shuffleboard, one of the game discs. And we have the two velocities given to us, and we're told the direction that they are moving in. We are asked to find the disc velocity relative to the Earth. Let's draw a diagram. We can see that we have our disc, and then we can have a ship. The disc moves forward relative to the ship. And then we're told that the ship is traveling in the same direction as the disc. So the ship we can also describe as moving forward, but the ship is relative to the Earth. We can imagine that the Earth is maybe the shoreline off to the side. We can also just call this the shore, since a ship is on water. So when we say relative to the Earth, we're relative to a point on the shore. So what that means is that somebody watching a ship go by on the shore sees the ship's motion in one direction, and we're trying to find out what will the disc look like. If this person on the shore has binoculars and they can see them playing shuffleboard on the ship, what will the motion of the disc look like relative to this person on the shore or on the Earth? Let's just get a couple of shorthand notations. Let's just say that disc we'll just say is D, ship will be S, and then Earth will be E. Always handy to have an Earth, because obviously there's Earth all around us, or there's ground all around us, so that's a very handy reference point to include, so we'll see the capital E used in a lot of these questions. What are we given in the question? We're told the disc velocity relative to the ship. So our velocity of the disc relative to the ship is equal to 4.2 meters per second forward. You know what? Let's use a capital F, because that's more consistent with what we've been doing. Then we're told the ship velocity relative to the Earth. This, though, is equal to 4.6 kilometers per hour, also forward. We will need to do a quick conversion, so we may as well do it now. I'm going to show you the multiple steps, but you can shorten this however you like. In order to convert from kilometers per hour, we can multiply by several conversion factors. Let's do the kilometers first. We need that in meters per second. We need to have meters in our numerator. So we put our conversion factor for meters in the top, and we want to find out how many meters are in 1 kilometer. My kilometers on the denominator will cancel out the kilometers in the unit from the question. There's 1,000 meters in a kilometer, but we need to also convert hours. So again, another conversion factor. In this case, they're going to be flipped because we want our desired units are going to be on the bottom. So we want to try and cancel that hour. So that means that we put our 1 hour in the numerator. And then we have to go from hours to minutes. Well, I'm just going to show you all the steps, but you can feel free to combine these. There's 60 minutes in 1 hour. So then doing this conversion will give us meters per minute. So we need to include another one. And there is, for 1 minute, you notice then that minutes in numerator, and the third step will cancel the minutes in the denominator of the second, and there are 60 seconds. in 1 minute. So this will give us our final answer in meters per second. Calculate that quick. 4.6 times 1,000, divide by 60, divide by 60. 1.2777, that's repeating, and that's now meters per second. Desired units, or at least same units as the other part of the question. That's all that's given to us in this question. What we are looking for is the disk's velocity relative to the Earth. So we're looking for the velocity of the disk relative to the Earth. For our analysis step, we can determine the VDE by examining what combination of the other velocities will give us disk relative to Earth. We can see that if we combine the velocity of the disk relative to the ship and we add that to the velocity of the ship relative to the Earth, my S ship is now the second script of the first velocity, and it's the first script of the second velocity. So they're both next to each other, right, quote unquote, and we have a D on the outside and E on the outside. So this should give us, or will give us, the disk's velocity relative to the Earth, just by adding them together. So then in our solve step, we use our equation from before to find our unknown. And we can plug in our values. 4.2 meters per second forward, or rather, what we'll do is we'll make sure the directions match. So the velocity of the disk to ship, that's forward, so we can leave it positive, as well as the velocity of the ship relative to the Earth. We can leave that positive also, because we can just define this direction, forward, as our positive. So then backward would be negative, but nothing's traveling backwards, so we don't need to adjust. Then, if I can squeeze it in down here, that means that we have 4.2 plus 1.2777, repeating, just to save space. That gives us 5.4777 repeating. That's meters per second, and the answer is positive, so that is 5.4777 meters per second forward. We can round our value. The question gave us 4.2 and 4.6. They each only had one decimal place, which means that our answer should only have one decimal place because we're only adding. We haven't done anything else other than multiply by these conversion factors, which do not count towards our significant figures. So rounding to one decimal place for this, we take a look at the 4, which is what we're going to round. Look to the right. The number 7 is above 5. Round up. .5 meters per second forward. It's a terrible bracket. What this means, the person standing on the shore sees the disc traveling faster than it's thrown. So to a person on the ship deck, the person playing shuffleboard, the disc looks like it's moving basically 4 meters per second in the forward direction. But to the person on the shore, we can see that apparently the puck or the disc is moving faster than the person has thrown it. So they can both be correct. Both their situations are right because they are each in a different frame of reference. So the person on the shore is we define the earth or the shore as one frame of reference, and we define the ship or the surface of the ship as another frame of reference. So depending on who is observing the motion, we can see different we can see different speeds or different values, which makes sense because if the ship is also traveling, you can see that the ship's velocity appears to add to the velocity of the disk. These things might be easy to picture, they might not be. I can post some videos that help describe this. Now, let's talk about finding the disk relative to the Earth. Excuse me, if the disk is moving opposite of the direction of the ship, or opposite to the direction of the ship, right? But it's the same velocity as part A. So what we can do is we're given a little bit of a different situation here. So let's draw our diagram again. So in this situation, we're changing. The disk is now moving opposite to the direction, so the disk moving backward now, right? Whereas the ship is still moving forward, right? And they both have their same velocities as before. So in this part of the question, what we're given now, a little bit different than before, is the velocity of the disk relative to the ship is still 4.2 meters per second, but now it's going backward. The velocity of the ship relative to the Earth, I don't need to do my conversion again, so I'll just write this value, 1.27 repeating. It's 277 meters per second, but this is going forward still. So if we said that it appears on the shore that it's going a bit faster, how do you anticipate this will look if the disk is now moving opposite the motion of the ship? We are looking for the same thing, or this is fine. We are still looking for the velocity of the disk relative to the Earth. And in our analysis, nothing has changed. Our equation still holds. We still just add them together. We just need to make a slight modification for direction, which we can just do in our solve step because that's where we've been doing that. So in the solve step, let's write this equation and let's account for directions going the other way. Since 4.2 meters per second is going backward, we will call that negative. And we'll add that to the positive ship Earth because that's traveling forward, which we defined as the positive direction. So we keep our same coordinate system as before, as we defined before. So another way of writing this, what I'm going to do is I'm just going to, yes, hang on. Let me move this quick because I can show you another thing. So I'll put this down here. I'll put it in the same spot, and we can just go up. Another way of looking at this is this disk ship. We can also say this is negative 4.2 meters per second forward. So putting the negative in front essentially flips the vector, right? So it changes the direction. So 4.2 meters per second backward is this vector for D here. If I make it negative, then I flip the vector and it points forward, but the magnitude of it has this negative sign to let us know that it'll be subtracted from another vector going in the same direction, if that makes sense. So the velocity becomes negative there. So that's all we've done in this. Now, showing you the example in the given step here is fine, but just make sure that you don't do the negative twice. So putting the negative in front here is all I need to do. The given here is I'm just showing you how that works. So what this ends up being is it's negative 4.2, right, meters per second, plus 1.277 repeating. So notice that I haven't done anything with the negative. I just wanted to show you how this negative sign works, how we can change the direction with backward and forward. So the negative in front of the VDS does not cancel this negative otherwise. You just do it in once or the other, right? And maybe what I can do is I'll put this in square brackets just to indicate that it's a little bit of an aside. So we've kept our one negative sign just to indicate that we've changed the direction. So we only changed the direction just once. And then we see how this adds. So negative 4.2 plus 1.2777 repeating gives us negative 2.922 to repeating. And that's meters per second. And again, since this is negative, we can say that this is the same thing as negative 2.9222 repeating meters per second forward, because you might have seen this vector notation where you have the negative in front, right? So this is negative, but because we've flipped both vectors to be in the forward direction, so our answer is still forward, but this negative value tells us that we would have to flip it, right? That the vector is not, that the negative magnitude points up, however, the positive magnitude, 2.9222 repeating meters per second, this positive magnitude is going backwards. So the resultant vector is that the disk appears to be moving backwards relative to somebody on the shore. Relative and again, 1 decimal place from the question, so that's 2.9. We look to the 2, it's a little bit below, or rather it's below 5, 2.9 meters per second backward. So you can see that if the velocity is sufficient in the other direction, it can actually still appear to be moving back. It doesn't look like it's going as fast. So again, in this case, the person standing on the shore sees the puck moving actually a little bit slower than the person who threw the puck, or the disc, sorry. Because the ship's motion is moving forward, so that motion moving it, forward appears to cancel out some of that velocity, some of that backward velocity of the disc, but not all of it. So standing on the shore, if you had binoculars and were watching them play shuffleboard, the disc would still look like it was moving to the left, even though the ship was moving to the right. And now, we'll add another condition. Find disk relative to Earth if the water is moving at 1.1 meters per second forward relative to Earth. Aha. So now we have a new condition. Assume the ship maintains its velocity of this relative to the water. So everything is going to be the same. And the other thing to mention of this is that the disk moves forward. Again, so we use our answer from part A for the disk moving forward. If I can just check to make sure I did that right. Yeah, perfect. So our diagram, because we've changed some conditions, so let's start fresh, right? You notice how each of these questions changes the question, right? So these are each kind of new. They're not building upon the same question. They always add something new. So in this case, not a bad idea to redraw and to do it given again. So the disk goes forward, right? The ship is moving forward also, maintaining its distance. Now we're saying we have a new thing. We're also saying that the water is moving forward. So we have a new thing, W, which will stand for the water. So we are given the velocity of the disk relative to the ship, which is the same as it was in the beginning, 4.2. Come on. Meters per second, and this is forward again. We have the velocity of the ship, this time relative to the water, not the Earth, but it's moving with that same 4.6. So it had its base, so the same velocity, but we're measuring it relative to something new, 1.277. 1.277 repeating meters per second. This is also forward, but this is now relative to the water. And then the new thing we are given is the velocity of the water relative to the Earth, which is 1.1 meters per second forward. We're looking for the same thing. What's the velocity of the disk relative to the Earth now in this situation, if we add another frame of reference? Our analysis hasn't changed much. We can still just add all these vectors together. Velocity of the disk relative to the Earth will be equal to the velocity of the disk relative to the ship. Add that to the velocity of the ship relative to the water. So our s's sort of cancel, right? Adding just these two vectors together will give us the disk relative to the water. And then finally, the velocity of the water relative to the Earth. You notice that these two vectors together will give us velocity of disk relative to water. And then we add that simply to the water relative to Earth. Therefore, the waters will cancel because they're both next to each other, and then the disk and Earth will combine. So we can see how that works. They're all moving in the same direction, so our solve step stays relatively simple. Disk Earth, we don't have to change the sign of anything because they are all going the same way, in our positive direction. Plug in these values, 4.2 plus 1.277, repeating 1.1. .5777, repeating meters per second. It's positive 6.5777, repeating meters per second forward. Excuse me. And again, 1 decimal place. So you can see that if we factor in the water motion, the disk appears to be going even faster relative to a person on the shore. Relative to a person on the shore, and then compared to the person throwing the disk.